Hello and welcome to the Daily Space. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Next week, the CosmoQuest staff is taking the week off as people in our team celebrate Passover and Easter, take a spring break, and in my case, just take the time to gather all the misplaced coffee cups that have accumulated in strange corners since we last took a week off. Today, I'll be covering the news solo as Beth has taken off early. The news, however, it just keeps coming. And our first story of the day is the kind of science that once I would have said is impossible. With light, there is no way to see what was happening in the universe prior to the release of the cosmic microwave background. Before that moment, the universe was opaque, and to our telescopes, completely hidden. If you ask me if we could ever observationally know anything about the universe's first 400 years, I would have previously sighed and said, I don't think so. That time is hidden, except for the echoes it left imprinted in the cosmic microwave background. What I hadn't counted on was gravitational wave science advancing the way it has, with people not just using detectors like LIGO and Virgo to measure black hole mergers, but also, now teams are using the timing of pulsars to detect the background perturbations in space caused by events that occurred in the early universe, in some cases before that CMB was released. Through gravitational waves, we can now imagine testing theories about what happened in the earliest moments of the universe. Researchers at the universities of Göttingen and Auckland created a simulation to look at the evolving structure of the universe in its first few seconds. They were able to see a complex network of structures similar in form to what we see with today's large-scale structure of the universe, only much smaller. According to a PhD student and lead author of this study, Benedict Eggmeyer, the formation of such structures, as well as their movements and interactions, must have generated a background noise of gravitational waves. With the help of our simulations, we can calculate the strength of this gravitational wave signal, which we might be measurable in the future. This is my favorite kind of theory paper. It is one that makes concrete predictions that can one day maybe be observed. What gets me about this work is the scale they were working at. The early universe was tiny. As Jens Nehmeyer explains it, the physical space represented by this simulation would fit into a single proton 1,000,000 times over. It is probably the largest simulation of the smallest area of the universe that has been carried out so far. Here's to hoping we one day learn how to record early gravitational waves with the same detail as the cosmic microwave background. Computer models are becoming more and more important to transforming all our measurements and ideas into things we can try and measure. This is as true for the universe as a whole as it is for our home planet Earth. We can't go back in time and see directly how the continents have moved and evolved over the planet's 5 billion year history. We can, however, find the world's oldest rocks and use them to place limits on what might have happened in the past. We've known for about a century that all the modern continents once fit together into a single supercontinent that we've named Pangaea. More recent work has found evidence of two older supercontinents in a 600 million year continental cycle. But has it always been the case? Has there always been this cycle? Without evidence, it wasn't something a model alone could sort. So researchers found the oldest rocks out there and went looking for magnetic evidence of how those rocks were once aligned with the Earth's magnetic field. Based on these new measurements and models of our world, this team concluded, to quote Zhang Li, we can almost rule out the existence of a long-lived single supercontinent before 2 billion years ago. Although transient supercontinents may have existed, more likely there could have been two long-lived clusters of cratons or supercratons before 2 billion years that were geographically isolated from each other, never forming a singular supercontinent. This work is published in the journal Geology with first author Yebo Liu, who adds, "This study surely isn't the final word on the debate, but it's certainly a step in the right direction, and we need to collect data from a lot more similar rocks to further test the hypothesis." This entwining of data and models is key. If a model doesn't have enough data, it is likely to miss important details. When it comes to understanding worlds, chemistry can play a significant role that is easy to forget. The Cassini mission to Saturn was able to catch samples of material from the geysers on the moon Enceladus and determine that the moon has salty subsurface seas. Gravitational measurements and heat calculations in combination with these salty measurements build up a picture of ice building up at the equator and melting at the poles, likely creating a gradient in salinity like we see in Earth's southern seas. When salt water freezes, the salt gets left behind in the unmelted water, making that water heavier and driving currents. This work is published in Nature Geosciences with first author Anna Lobo, who explains, knowing the distribution of ice allows us to place constraints on circulation patterns. Co-author Andrew Thompson adds, understanding which regions of the subsurface ocean might be the most hospitable to life as we know it could one day inform efforts to search for signs of life. Data and models working together. This is how we figure out the universe. After the break, we're going to look at weird earthquakes here on Earth and what they teach us. And later, we're going to look back at Viking experiments to look for life on Mars that started 50 years ago Saturday. Stay tuned. I love a good science mystery, especially when it involves earthquakes. I prefer volcanoes. Earthquakes will do. Back in 2018, there was an earthquake in the region of Indonesia that unfortunately caused deadly tsunami, even though it wasn't the usual type of fault system that causes tsunami. Scientists analyzed the quake and found that although the fault is technically a strike-slip fault where two tectonic plates slide past each other, this fault was at a steep angle, so the sudden slippage of the two plates displaced enough water to set off the tsunami. Now, a pair of earthquakes in the Alaska-Aleutian subduction zone has given rise to a new mystery. You see, the first quake made sense. It happened as subduction quakes do, with one plate slipping below the other. And it happened in an area where quakes have happened before. A lot of things were happening here. The second quake, well, that one didn't happen as expected, or where a quake would even be expected. When it comes to earthquake fault zones, a lot of them have what we call a gap, a region along the zone where quakes do not tend to happen at all. It's considered an unlocked or decoupled region. The rocks aren't sticking together, so when the plates move, they move smoothly. No quaking going on. And this second quake in October 2020 not only occurred in a region of the subduction zone known as the Chugmagan Gap, it was also a strike-slip earthquake, not a subduction earthquake. A new paper analyzing these two earthquakes was published in Science Advances this week, and as lead author Kevin P. Furlong explains, there must be a fault in the subducting Pacific plate, and we can't see it. In the oceanic crust, there are strike-slip faults that developed at the mid-ocean ridges. This fault in the Chugmagan Gap could be a relic of a fault from the mid-ocean ridge, activated in a different way. It appears to be in the correct direction. In more weirdness, that second quake also caused a small tsunami. Furlong and his co-author Matthew Herman modeled the two earthquakes along with the tsunami. And they found that the reason the second quake occurred is because that section of the fault zone is unlocked. Herman noted the potential for unusual earthquakes in these regions makes sense from our computational models. but is still pretty counterintuitive. Making the expected kind of earthquakes less likely actually makes other types of big earthquakes more likely. So it turns out that we don't completely understand all the nuances involved in plate tectonics. That's not a surprise. Earth is big, it's a complicated world, and we continue to analyze all the unusual events to dig at its secrets. Knowledge is powerful, and in this instance, knowledge could save the lives of people living in the region. The more you know, and all that. Next up, we will look for dark matter before looking back at historic missions throughout our solar system. Don't go away. One of the great mysteries of the universe is what is dark matter? The bizarre material doesn't interact with light, but gravitationally throws light and mass around as it interacts with things at galaxy and galaxy cluster scales. People keep trying to identify dark matter with specific theorized particles and keep looking for new ways to either make it go away with new observations or pinpoint it exactly. So far, dark matter refuses to be seen and refuses to go away. In the 1990s, there was some evidence that dark matter might be weakly interacting massive particles, or WIMPs. This came from an Italian experiment that looked directly for the WIMPs colliding with sodium iodide in a detector. It was, it was expected that if WIMPs are dark matter, then they will be everywhere, and the detector would act like a windshield in the rain, catching the WIMPs as our planet goes through the galaxy. Specifically, it was expected that the Earth's motion would seasonally change the rate at which WIMPs are detected as we moved with and against the sun's motion around the sun, just as the amount of rain changes on the windshield with our velocity relative to a storm. In 1998, the Italian team announced detection of the expected signal. And in the 20 plus years since, teams around the world have tried to find further evidence of WIMPs, to no avail. Most recently, a Spanish team, a NIAS collaboration, replicated the experiment in its entirety and found nothing, proving once again that to truly believe a result, you need to replicate the result. This seems to indicate WIMPs are not the dark matter particle we need. And these lack of detections bring into question more than just the possibility of dark matter being WIMPs. WIMPs are a key prediction of the supersymmetry model of particle physics. No WIMPs could mean no supersymmetry, which means that a whole lot of other predicted particles, which admittedly have no evidence, probably really don't exist. Now, I personally am not at all bothered by this. The universe is what it is, and we'll figure it out when we figure it out. There are, however, a lot of physicists who want there to be an underlying theory that explains why our universe has the specific set of particles that it has. Supersymmetry is one of the more advanced and accepted possible theories that tries to explain why we have electrons, protons, and neutrons, why there are the quarks we see and not some other set. It's a complex theory I can't pretend to say I completely understand. And now it is looking more and more like it is a theory that doesn't match reality. And that puts us back to having a universe that exists for reasons we just don't know. And as confusing as dark matter is, there are other things that we need to figure out about it. Regular matter, like dark matter, isn't always cooperative about being understood either. We have understood from a variety of observations that 5% of our universe should be made of the same normal baryonic matter that we, our computers, and our tables are made of. But we can only account for about half of that amount in surveys that have added up the amount of mass in stars, planets, and other stuff in and around galaxies. Now, a new study published in the monthly notices of the Royal Astronomical Society in a trio of 3 papers by researchers Carlos Hernandez Montego, Jonas Chavez Montero, Raul Agula, and Giovanni Arrico, looks purely at the velocities of galaxies to see how they gravitationally interact, and uses this data to look for the pull of otherwise invisible gas. According to Jonas Chavez Montero, most of this ordinary matter is invisible to us because it is not sufficiently hot to emit energy. However, by using maps of the redshifts of the galaxies, we find that all of this matter fills the space between them. To distinguish between dark matter and regular matter, they looked for the signature of electrons scattering light from the cosmic microwave background. These results look good, and I feel safe saying half the regular mass is probably hiding in the spaces between galaxies. I'm okay with this. The universe is what it is, and we're going to learn about it one instrument, spacecraft, and computer model at a time. After the break, we're going to talk about early missions to our solar system and the life people don't want to admit at least one of these missions may have found. Stay tuned. For reasons I can't explain, it sometimes seems like historic moments pile up around certain weeks of the year. We mourn in late January for too many astronauts lost. New Year's and the 4th of July celebrate the great landings and flybys of so many missions. And this weekend, inexplicably, brings us two anniversaries in planetary exploration. On Monday, we celebrate the 1974 flyby Mercury made of Mariner 10. If you try Googling this mission, you will learn the Mercury car line has their own Mariner edition, and I really hope this is a callback to this great little spacecraft that left the Earth before I was born. Mariner 10 was the last of its line of spacecraft. This series of missions made the first flybys of all the worlds in the inner solar system, entered orbit around another planet for the first time, and set us back the crushing news that Venus is too hot for life and Mars is a desert world without canals or seas. Science fiction was forever changed by these missions, and the modern era of planetary science was started. From Mariner 10, NASA moved on to developing the Voyager and Viking programs, and the technology of these missions eventually evolved into the Cassini mission. When Mariner 10 reached Mercury, cameras took what for 33 years would be our only close-up images of Mercury. Growing up, these images appeared as they do in the image behind me to the left, mosaic together with poorly matched backgrounds. Remarkably, these images would go on to reveal new science thanks to modern image processing software like Photoshop. In the years leading up to Messenger, a mission that flew to Mercury, these images were reprocessed, and with that new reprocessing revealed amazing details thanks to modern methods, showing that sometimes technology can reveal more than we imagined, even in data we already had. Tomorrow is the 50th anniversary of the start of the Viking experiments to look for life on Mars. To be clear, those actual experiments occurred in 1976, but their origins go back to a 1971 lab experiment to see if conditions simulating those on Mars could produce organic compounds. And those experiments showed they could. Those results led to the inclusion of 3 different experiments on the Viking landers that looked to simulate interactions with microbes in various ways, experiments that were inconclusive, with one researcher, Gilbert Levin, saying life had been found, and that in analysis of images, even lichens could be seen on surrounding rocks. These results continue to be controversial. The result that seemed to indicate there was life is one in which they provided nutrients to soil and looked to see if that soil outgassed materials that incorporated that stuff that had been fed. And if it did, here on Earth, that is a sign of life in the soil. And we saw this on Mars. But because the other experiments that were run did not also find life, it has been easier to simply say either life was not found or the results were inconclusive, leaving poor Levin to a lifetime of screaming to the wind, yes, there is life on Mars, and a constant appeal to replicate these experiments, a replication that still hasn't been done. Today, the Perseverance rover is out there not looking for these kinds of active signals of being able to interact with today's life. It's instead out there looking for fossils. But I hope someday soon, someday before Levin, who ran the experiment in 1976, passes away, I hope we will have further understanding of just what happened with his experiments that all started in a lab 50 years ago tomorrow. This has been the Daily Space. If you liked the show, please consider joining our Patreon community at patreon.com/CosmoQuestX. We are part of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. You can find more information on all our stories, including images, by visiting dailyspace.org. See you Tuesday. Bye-bye.